Hello, everybody. We are on to the Pons today. And up until 2019, when I was giving this lecture, it was a single hour. And in retrospect, I feel sorry for everyone who had to go through that because it was a ridiculous amount of information. Last year, or 2019, I split the lecture in two, and that alone was a big improvement, but I didn't have time to expand the first part to be a complete, separate, independent talk. But over the last 3 days, I've spent a lot of time on it, and I'm looking forward to giving this because it's going to be quite different than the ones in the past. So on we go. Here's our outline, now in two parts. The line separates us. Today, we're going to talk about the caudal pons and the vestibulocochlear nerve and its nuclei. And then in the next hour, which will be next week, we will talk about the cranial nerve nuclei in the rostral pons, as well as the rostral pons itself. So to begin, we are now in the caudal pons. We just, of course, left the medulla last week. And we're going to start with the dorsal pons, the tegmentum of the pons, and then we'll get to basis pontus. It continues what was going on in the medulla. That is, it contains reticular formation, tracts that are ascending and descending, and the cranial nerve nuclei, although, of course, the cranial nerve nuclei are now changing. The reticular formation within the tegmentum of the pons is routinely divided into caudalis and oralis. The tracts that we'll look at that are running through are the medial lemniscus, of course. We're going to see that become horizontal. We're going to spend a few minutes on that. And then what we're not going to do is discuss hearing, which is an enormous part of the caudal pons. We have two separate lectures later in the course on hearing, but we will see the trapezoid body and other parts of the hearing system. We'll see the MLF, where it belongs, I want to say, in the midline near the fourth ventricle. We'll look at the central tegmental tract and the cerebellar peduncles, which we'll have to spend some time on because they're huge. And then over the course of these 2 hours, we will look at cranial nerves 5 through 8. Today, we will look at the vestibular portion of 8 in some detail. On the surface, let's just start up here at the superior cerebellar peduncle. That's going to be running through the pons. So here's the pons. Here's the pontomedullary junction. And almost off the screen is the pontomesencephalic junction. We're looking then at superior cerebellar peduncle, which is traveling from the cerebellum upward. We'll look at that today and next time. Here's the trigeminal root. We're not going to, today, we will not talk much about the trigeminal root, a little bit. Here are these oblique pontine fibers, which ends in the pontobulbar body. Bulbar usually refers to medulla, but in this case, I'd almost like, I don't like this name at all. It would be better if they just, because all this is, the nucleus that's down here is simply a extra pontine continuation of the pontine nuclei, and we're going to talk about them in a lot of detail today. Here comes the abducens nerve. There's a facial nerve over in the CP angle, facial nerve, intermediate nerve, right? And of course, the vestibular nerve, glossopharyngeal, and all the others, but that's medulla. We don't want to talk about that. The cochlear nerve coming in, the vestibular nerve, again, we will talk about in some detail. And this massive cut section, which we're going to try to understand as well as localize, but try to understand today, is why is the cerebellar peduncle, the middle cerebellar peduncle, so darn big? We're going to talk about that. In an axial view through the pons, here, okay, we'll start up here, the cerebellum. Here are the cerebellar peduncles. Here's the superior, we saw running on the surface, the inferior, which we talked about last time, and they are embedded in the middle cerebellar peduncle. They're embedded within it. That's how big the middle cerebellar peduncle is. This is just a sort of dorsal pons, meaning the tegmentum, again, of the pons, and the ventral pons, meaning the basis pontus. And nobody uses these terms very much. It's a tegmentum and the basis pontus. We see here the lateral lemniscus, which is, we're not going to talk about because it's a part of the hearing system. Here are the pontine nuclei. Again, we're going to talk about them a lot. You recognize the corticospinal tract, no problem. You can see the course of the seventh nerve, by the way, going around the sixth nerve nucleus, right? And the facial colliculus. And then we'll come back to that a little bit. Here's the MLF. Like I said, we're sort of where it belongs, where we expect it to be. Here's the medial lemniscus. Almost like I can never get rid of the image of pinball flippers. Maybe it reflects my adolescence, but those to me like pinball flippers. And then this is the superior olivary, again, sound, nucleus 7, we'll talk about next week. Here's the central tegmental tract, okay? That is basically a gustatothalamus tract, if you will. That is, it's from the rostral half of the solitary nucleus, the gustatory nucleus, if you will, up to the thalamus. That's what that's doing. I'm not going to talk about it much today, other than what I just did. This is the caudalis reticular formation. Here's the spinal trigeminal nucleus and its tract, which we dealt with in detail last week, and no further discussion today. And then the vestibular nuclei up here, and we are definitely going to speak about them in a lot of detail today. Here, I don't need to go over these over again, but this is obviously a Nissl stain. This was a cartoon of a Weigert stain. Here's a cartoon of a Nissl stain. Probably is actually a Nissl stain. And focus here on how dense the cell bodies are in the basis pontus. These are the pontine nuclei. They are mammoth. Those are what are going to explain the enormous size of the middle cerebellar peduncle, but we're going to talk about them in detail. Here's the sixth nerve nucleus, and here's the nucleus of the medial eminence. Now, I spent a lot of time searching this and cannot find an answer as to what they are. So this is the tract in this Nissl stain. The absence of cells indicates the facial nerve traveling through and around it. That I get. And I would gladly have said, well, it split the sixth nerve nucleus, but the cells don't look the same. They're not the same size, they're not the same density. I wondered if either Shruti or Juan or anybody else knew what the nucleus of the medial, not median, but medial eminence is, because I cannot find a reference on the internet. So if anyone can, let us know next time. But I mean, I've spent hours, really seriously hours looking, cannot find a single reference on what these are. Trix and Carpenter did not reference it, nothing. I don't even know what it is at this period. Anyway, we're back into the reticular formation. We have large cells, gigantocellularis. We have small cells, parvocellularis, that sort of thing. But you can see, and again, we discussed, if you will, the teleology of the reticular formation in our last lecture. Here's the nucleus, by the way, of the trapezoid body. These again, solitary, the superior olivary. We'll talk about those next week or in a separate lecture. Here, where I want to focus, this is a one-off on the medial lemniscus. That is, this slide stands alone. The focus is on the medial lemniscus. Gracilis and cuneatus, of course, right? The medial lemniscus pathway is, in the end, the termination of the posterior columns. We saw those. They end the nucleus, gracilis and cuneatus. We looked at that last week. We are now looking at the secondary nuclei, which go from nucleus, gracilis or cuneatus, all the way up to the thalamus, and that's the medial lemniscus. However, I wanted to show you the topography of the medial lemniscus in this slide. You don't need to focus on any of this, except look at where the red arrows are. So up it comes. This is what we're used to. And then here, when the medial lemniscus is medial and oriented medially, right? This is gracilis, so this is coming from the leg, all right? These fibers are ventral in the medial lemniscus. And then, as the medial lemniscus rotates, this is a very complex rotation. It's not like the flippers of the pinball machine. They're not pinned at the site of rotation. In fact, it's closer to a deslizza. It's a sliding of the dorsal portion ventrally, and then a swinging outward of the ventral portion laterally. So that's what's going to happen. So see, here's the ventral portion. Here are the legs in the ventral portion. But once it's horizontal, the legs are out laterally. And that is, again, the opposite of the way it is in the cord, where the legs are the most medial portion. So this is quite a rotation that occurs, and the corresponding portion of cuneatus is simply that it begins in the dorsal portion, while the medial lemniscus is medial and is vertically oriented within the axis of the medulla and pons. And then basically the fibers from the arm, which are dorsal, become medial once it swings out laterally horizontal. So that's all. It's not that complicated, but it's so different that I felt like we needed to deal with it. And here's a beautiful, again, Weigert stain. And here we are. So the medial portion here would be from cuneatus, if we're dealing with the arm, and out here laterally would be from gracilis, that is dealing with the leg. And that's all. The rest of it is stuff that we've already talked about. We don't need to go over it. Okay. Before we leave the tegmentum, are there any questions that anybody wants to ask? All right. So now we move into basis pontus. And what's in basis pontus? A lot of longitudinal fibers. There's the corticopontine, I want to say corticopontine cerebellar pathway. That's what we'll call it further out. There's the corticobulbar pathway going from the cortex down to the cranial nerve nuclei. The corticospinal pathway, the corticospinal tract, the pyramidal tract that we're familiar with. This is just the outline of it, okay? And here come the pontine nuclei. So what do the pontine nuclei do? We looked at them on that axial Nissl stain. They send the fibers to the contralateral cerebellar hemisphere. And those are the transverse bundles that we see in basis pontus. The pontine nuclei are the major pathway for the cerebral hemispheres to enter and access the cerebellum. This is a disynaptic pathway from remember all that that we looked at in one of our earlier talks on the cerebral hemispheres, the corona radiata going down into the cerebral peduncles of the midbrain, right? Internal capsule, cerebral peduncles. And then, and to anticipate, the corticospinal tract was so small. It's like, what happened? What happened to all those fibers? This is what happened to them. They synapse on the pontine nuclei. We're going to look at some numbers in a minute. And then the pontine nuclei cross the midline and go to the contralateral cerebellum. All right. That is what creates the enormous middle cerebellar peduncles. The pontine nuclei are not only from the corticoponto pathway, that is by far the major pathway, but the reticular formation also has significant input into the pontine nuclei, and also the superior colliculus, dealing primarily with eye movement, are also going to be going into there, and that's all of that then is going to be coordinated. Now, I don't normally put in this many words, and in fact, I edited both of these paragraphs, but they are so well written. I've given a reference here. They are so well written that I couldn't help myself but to include them here for you to read. So what we have been discussing is the question of the cerebral peduncle is so huge and the pyramidal tract is so small, what happens? So here are the numbers. Each cerebral peduncle, on each side, contains 21 million fibers, okay? But there are less than 1 million fibers in the ipsilateral pyramid. It doesn't matter that they're decussating or not. They're symmetrical. So you got 21 million going down to 1 million. And that's what's going on. Where do the remaining 20 million go? Well, they stop off at the reticular formation. A lot of those having to do, especially with eye movements, but other things, singing and other things that we do make use of the reticular formation. So it's a lot of stopping there, okay? And of course, they go to the motor nuclei. Those are what we call the corticobulbar pathway to the facial nucleus, right? Never to the ocular motor nuclei. Okay, never. Those are always through the reticular formation, but down to 9, 10, 11, 12. I mean, we've talked about those. So that's a corticobulbar pathway. But the majority of them, the vast majority, end in the ipsilateral pontine nuclei. And each pontine nucleus, each half, okay, each pontine nucleus of one side contains 12 million neurons. So these are huge. All right, these are huge, and that's what's going to project into the middle cerebellar peduncle. Now, count it up, guys. There are 20 million fibers that we're trying to account for. Some of them are part of the cortical bulbar pathway. Let's make believe it's 2 million. So we have 18 million fibers synapsing down onto the pontine nuclei, but count it up, okay? Right? There are 12 million fibers that are heading out. So there's some convergence that's going on, and frankly, there's also some divergence that's going on. So we're not going to talk about what the pontine nuclei do. That would not be anatomy. That would be complex physiology, and we're not going to be dealing with that. But there are your numbers. So the to stay with it now, the second part of this is that this corticopontocerebellar pathway simply dwarfs the corticospinal tract. So when you're looking at the cerebral peduncles, don't be thinking corticospinal. That's mostly corticoponto, right? In most species now, some more detail. In most species, this pathway originates from the central sulcus. I think this tells you a lot about what the cerebellum is doing. So go back in phylogeny just a little bit. Most of the corticopontocerebellar pathway is coming out of the Rolandic fissure. It's going to be the premotor, so the precentral gyrus, also the postcentral gyrus. Okay, so it's mostly going to have to do with movement, right? It's mostly movement. And in other species, lower in phylogeny, there will be input from the visual, limbic, and association areas, but not very much. Come up into the vermis, though, excuse me, reading while I'm talking, come up into the human, all right, and these association areas, visual areas in particular, but also even some limbic areas start to populate the pontocerebellar, the cerebroponto, the corticopontocerebellar pathway. So you're starting to see some cognitive and higher functions that are not pure motor, or that are higher motor. Maybe they are motor, but they are more goal-oriented motor and things like that. But the cerebellum really then is motor in its origin, a coordination of motor, but fundamentally involved in movement. And I'm sure that remains true in the human, but it becomes a broader kind of movement. The other thing that was interesting from this talk on cerebellum by Todd is that, so we know that the vermis has to do with gait and station, trunk, extension of the body, standing up in plain English. And we know that the legs are paramedian to the vermis. So that was good. And we think of the hand and other cognitive functions as more lateral in the cerebellum. But what I thought was really nice was the way they presented, and that is the fibers of the pontine nuclei, which end in the vermis, which end in the paramedian, are congruent with the inputs from the spinal cord. That makes sense, of course. So with the incoming information from the spinal cord and the downcoming information from the cerebral hemispheres, from the Rolandic area of the cerebral hemispheres, they're congruent. That makes so much sense. And again, gives you some insight into the function of the cerebellum as taking this ascending raw data, not raw, really raw, but mostly raw data from the spinal cord, and merging it with the highly processed information coming out of the central area, the Rolandic area. Because remember, we will talk about later when we talk about movement as an anatomic principle, that the precentral gyrus has all of the cognitive function of a Morse code key. That's it. It's a da-da-da, da-da-da. This is what's going on. This is what I was told to tell you to do. There's not a lot of integration. It's a Brodmann's area 1, right? It's all pyramidal neurons just sending information. That's what I say. It's like a Morse code key that is integrated a lot of information. We'll talk about it in the future. At any rate, and then the lateral cerebellar hemispheres really are integrating information from lots of different cortical input from the premotor area, the somatosensory areas, and even the association areas of the cerebral cortex. And the association areas are sensory modality neutral. They don't care. They are goal-oriented activities. And the cerebellum is going to play a role in these goal-oriented activities as well in the human, but usually not in other species. Let's look at the Pontine nuclei a little bit more simplistically for a minute. Let's get away from the concept. They represent, they receive a monosynaptic glutamatergic cortical pontine input, just what we were talking about from the precentral gyrus and its relatives, okay? And then within the nucleus also, as virtually always in the nervous system, are a lot of GABAergic interneurons. So that's sort of what you would expect. The visual input, and again, I think all these things are really interesting. The visual input is mostly from peripheral vision. There's no central vision coming in. We're not reading with the cerebellum. We're taking a swing at a baseball, playing tennis, all right, killing the damn mosquito on our lawn, all of that stuff, or red lantern flies, as the case may be right now, right? Okay, so that's what we're doing. And then in addition, you have the brainstem reticular formation and also the mammillary bodies, interestingly, synapsing onto the pontine nuclei. The pontine nuclei on the efferent side, because this is really organized, right? Afferent, efferent. The efferent pontine nuclei are going to the cerebellum. They provide most of the mossy fibers. That will make more sense when we talk about the cerebellum and the mossy fibers. But that's where the data is coming from. Remember, we saw the climbing fibers, which sort of say, wake up, pay attention, right? And then pay attention to what? Okay, here it comes. And here comes all the detail from the mossy fibers. Most of that mossy fiber information is going to be coming from the pontine nuclei. Not all of it, but most of it. It will be all of this information going in is going to be functionally diverse, like we've been talking about, linking the cerebral cortex with subcortical nuclei, and also all of this information coming together in the cerebellar cortex. And we will see this when we get to the cerebellum. This is a good slide for this stage, for what we're talking about right now. So let's follow it down. Green is the corticospinal tract. So let's just look at it, right? Here we are on the, say it's Rolandic, and we come down, and we're in, corona radiata, internal capsule, cerebral peduncle, base of Pons, just going right through it, paying no attention to anybody, going down to the decussation and descending in the corticospinal tract. Nice and simple, okay? Well, let's look at this guy, all right? Here comes a guy supposedly right next to the other, and it's descending through the corona radiata, through the internal capsule, through the cerebral peduncle, but it jumps off in the pontine nuclei, right? So it jumps off in the pontine nuclei. And then what does it do? Well, it crosses the midline, all right? And it goes out into either the cerebellar hemisphere, or some of it, not a lot, some of it goes to the deep nuclei. Now let's continue to follow the one that went into the cerebellar cortex, because this is much more typical, and that is out it goes down to the nucleus. And since we're out in the lateral hemisphere, it goes to the dentate nucleus. I don't think you could see very easily, so I just put this in here to emphasize that there's a synapse here. We're not going all the way back up, God forbid, from the cerebellar hemisphere to the thalamus, no such thing. Okay, we can't do that. Those are connections that don't exist. Instead, the cerebellar hemisphere talks to the dentate nucleus, and then you have the dentate nucleus sending information, first of all, to the red nucleus, the dentato-rubro pathway, all right. And then we have from the dentate to the thalamus, the dentato-thalamic pathway. It's going it's going in a certain sense, Puna, it's going back where it came from. Remember, we talk about the double cross. We talked about one double cross last week, but there's another double cross. Okay, it's going right back where it started. It is, sorry, this would be, so if this, let's assume this is the descending left cortico-pontocerebellar pathway. This will be going to the right cerebellar hemisphere and the right dentate embedded within it, right? That does not cross, that is just an inflow. We'll see that in the cerebellum, but it just flows directly. That white matter just engulfs the dentate, all of the nuclei, but especially the dentate. And then here's another one where, so then this one that's coming up then goes into the thalamus, and then of course, right, the thalamus sends it out to the back to the cerebral hemisphere. And that is another pathway that cannot happen. No dento-cortico pathway. These are the obligate. I was thinking about it. This slide really made me think again about translation, language translation, which I'm doing all the time these days. But it's as if staying with this for the moment, it's as if the cerebellar cortex simply doesn't have the language of the red nucleus. It can't talk to the red nucleus. It can't talk to the thalamus. It doesn't know the language. In this case, what's the language? Well, it's still bits and dots, it's ons and offs, but with frequencies and patterns, right? Of a different, possibly a different chemistry. All of this requires a translation, literally a linguistic translation of the language of the cerebellar hemisphere. It doesn't work. It won't translate into the language of the cerebral hemisphere. In order to do that, it has to go through two translations from the dentate to so the dentate does speak the language of the cerebellum, but it also speaks the language of the red nucleus and the thalamus. And the thalamus speaks the language here. It understands this language and it can translate it into this language. I think as a functional thing, that's one of the lessons to come away. And we'll encounter that when we talk about the somatosensory pathways. We're going to see it multiple times within the very different somatosensory pathways that we're going to talk about. And so red line out here, just look, here's the corticospinal tract. But it's too big to be the corticospinal tract. This is the corticospinal, corticobulbar, corticopontine for the lower pontine nuclei. Here are your pontine nuclei. Okay? All right. I hope that's clear. And again, this was a slide that we showed earlier, and you can see the, sum of the 12 million, just in this half is 12 million. Notice also that the pontine nuclei go all the way out into the middle cerebellar peduncle. This is a big pathway. This is a major part of the brain. This is not a trivial piece here. I like this slide. I picked this slide up a couple nights ago, and this tried to lay it out for you that there is a topography within the pontine nuclei. I like that. So it shows you in this cartoon. It shows you these are light gray, so these are meant to be the descending pathways. Okay, and then here's a premotor pathway. So this you wouldn't find in most other species. Here's the motor pathway. This will make up the bulk of most other species. Here's a little bit of somatosensory that would be present in other species. And then here's the posterior parietal, would not be present in other species, but way out lateral. So very core-like, the older phylogenetic motor, somatosensory, surrounded by premotor and posterior parietal. And then, oh my gosh, here's a big area of visual, all right, looking and watching and learning and perceiving and exploring our world around us, and not just sticking our tongue out and catching the fly, which is important. I don't want to minimize catching the fly to the frog. It's very important. Where would frogs be without that? They'd nowhere. Okay. All right. Let's just again stop for a second. Then I cannot say how different this is from prior versions of this lecture. And I don't know what I was talking about in prior versions, trying to everything that we just said, I probably would have said in 10 minutes in the last lecture. It was inconceivable to me at this point. It's like, what was I doing? Poor Dr. Prabhu. She was the one who received this. Like all of our heads were spinning by the time we were done with it. All right, let's move on. We now have another new and major division. This is going to go on for a while. This is what really expanded in this talk. So we're going to talk about the vestibulocochlear nerve and nuclei. Okay? So the cochlear part of the vestibulocochlear nerve is concerned with hearing, and we're not going to talk about it any further today. We're going to have two big lectures on this. A lot of time out in the anatomy of the ear itself. I added in last night a major portion on the anatomy of Scarpa's ganglion, which it wasn't even present in the last talk. So the vestibular portion of the vestibulocochlear nerve, eighth nerve, addresses equilibrium and orientation in three-dimensional space. That's what we're going to be talking about now. There are bipolar neurons. Someone asked, Puna, I think, was asking last week about bipolar neurons. Did you ask about bipolar? It doesn't matter. Someone did about bipolar neurons. There are true bipolar neurons in Scarpa's ganglion. I'm going to use the term Scarpa. I don't know why, because I like to. You could call it the vestibular ganglion. The problem with vestibular ganglion is we have vestibular ganglion, we have vestibular nerve, we have vestibular nucleus, we have a lot of different things, and they're all called vestibular. And I think it actually helps to give it a different name, but it doesn't matter what you call it. It's one or the other. Within the ganglion are the hair cells, are the bipolar neurons, synapse on the hair cells of the vestibular sense organs, that is the macula of the utricle and sacral, and the cristae ampullaris of the semicircular canal. So you really have two things coming in. Within the vestibular nerve, and within Scarpa's ganglion, which give rise to the vestibular nerve, you have a superior division and an inferior division. This is going to get really crazy as these things. This is in many ways worse than the brachial plexus, okay? Because it doesn't follow function, okay? It's not going to follow function. We're going to have different things. It follows sort of convenience, okay? And it's a conduct. I mean, you know, this whole this whole apparatus embedded within the petrous bone is three-dimensional, really, really complex. I'm going to bring you, I have a gold cast of the cochlea that I will bring you, that I was given as a going away gift from the anatomic group at Stony Brook, as a going away gift after 21 years of interacting with that anatomy group. That's why I say this was living, breathing anatomy to us, and this was one of my treasures upstairs. It's from the Diener of Stony Brook. And anyway, this is going to come and go. And so here, and this is what I'm saying, in the superior division of the vestibular ganglion, we have utricle and superior and lateral semicircular canal. But in the inferior division, we have the sacral and the inferior canal. It's like, that doesn't help. That really isn't very useful. So this is a wonderful diagram that I found. Let us begin down here. We have a transmission EM of the otoliths, which occur in the macular area of the utricle and sacral. I don't know which this is. It could be either. That makes no difference. They would look the same when I say it makes no difference. And here's an ampulla, the cristae ampulla. And this is going to sit in the ampulla of the semicircular canals, like here, all right? And when you turn your head, right, the cristae is stuck where it is, but the relative and the fluid is going to hold still. But the petrous bone is moving with the rest of our head. And so that will create, through inertial movement, a deflection of the cristae. All right, and that will cause that will be detected as angular momentum by the cristae. So these are going to be for linear momentum and status equilibrium. Okay, as gravity grabs these things and they lean against the hair cells of the macula, but the cristae will be deflected by rotatory movement for angular acceleration. Those are the two pieces of information that the vestibular apparatus is going to provide to the brain. Okay, static equilibrium, and then linear acceleration and angular acceleration, or acceleration and therefore momentum. Really, it's the acceleration is what they're detecting. That's the physiology of it. At any rate, this is the apparatus, and you know, here we have just there's a whole bunch of different parts. All right, and they're coming together. And here I put in here Scarpa's ganglion. It really should be ganglia, but no one calls it this story. I looked this up. No one calls it Scarpa's ganglia. They should. Because there's two of them, superior and inferior ganglia, which make up the Scarpa's ganglion. Which anyway, and then this is going out the superior division, and this is going out the inferior division. So all of this is in this diagram, which wasn't even in the last talk. This, however, was. And so here we're entering the internal auditory meatus is really where we are here. And that's why you see facial nerve and nervus intermedius, I think Bell's palsy. And then here's the anterior and lateral semicircular canal, which obviously are big three-dimensional structures, which we're not showing, the utricle and the sacral, utricle. And the posterior canal. And that's why I say this this doesn't even work. And then the other thing is there are some interesting on this diagram caused me to look up, I didn't know, but Hardy's nerve and the vestibular cochlear anastomosis of Oort. These are things that I had not been cognizant of, which I'm now. And that is there are communications, which I don't know if they're really, whether they're functional communications or simply it just takes a trip along with them. And I don't know the answer to that yet. I'm running out of time last night. Here we are with we are now moving into the vestibular nuclei. So let's introduce the vestibular nuclei and then we'll hook them up with the vestibular nerve. The vestibular, there are 4 divisions. There's the inferior division, the lateral division, also known as Dieter's nucleus. You will see that term, so I'm using it. The superior division and the medial division. The inferior division is in some anatomic references also referred to as the dorsal division. Okay, the inferior division, most refer to it as inferior. The inferior division receives mainly saccule and utricle. Good, thank you, that makes sense, right? So when we get to the nucleus, the nerve and the ganglion don't make a lot of sense, but the nucleus makes functional sense in most cases. So, and I'm gonna try to emphasize that as we go. So this is obviously for a static equilibrium and linear acceleration. So good, inferior. Okay, lateral is going to, however, receive from the utricle, which, all right. Then the superior is going to receive from the 3 semicircular canal. Good. Superior deals with angular acceleration. Good. And the medial, which is the largest division, you're right, that's an answer, is going to receive both semicircular and utricular information into medial. In addition, the vestibular nuclei receive direct vestibulocerebellar fibers, or it should be cerebellar vestibular fibers in this case, which are going to come very much from the floccular nodular lobe and the nodulus. So this is, remember, we talked last time about we haven't really, and of course, when we get to cerebellum, we'll look more, but the archicerebellum, the oldest portion of the cerebellum, which is sometimes referred to as the vermicerebellum, which should, if you remember back to the cerebellar nuclei, you remember we looked at, EDFG, so, or DEFG, the dentate and baliform, vestigial and globose. The vestigial was numeric or alphabetically out of order because that's the oldest one. So there is going to be some input from the vestigial nucleus, so the cerebellum, directly to the vestibular nuclei. You're going to have a vestibular cerebellar input into the vestibular apparatus. This is one of the early slides that I had. I don't know that it does very much, but it just shows you different portions coming in through the canal and then coming through, and then here's the vestibular tract, and then that diverges into a more sensible. And these colors are helpful. This mixing that we talked about works in this color scheme. Again, watch out for different naming conventions. This is a nice fluorescent stain of showing you in place the anatomic vestibular nuclei with the vestibular nerve penetrating and ramifying within the vestibular nucleus. So I like that, and that's true anatomic, and there's a diagram so you can see what's going on. There are other afferents that are coming into the vestibular nuclei. They are not simple structures at all. And so, again, they're going to be integrating a lot of incoming information. Surprisingly, there's a lot of information, well, not surprisingly, coming from the cerebellum, but there's a lot of information coming from especially the reticular visual and somatosensory system. And that sort of makes sense if you want to integrate vision and somatosensory with balance and movement, and you do. So, and by far the most important are going to be these old projections out of archicerebellum. And here in some of the detail, you have the vestibular cerebellum, which is flocculus, nodulus, the ventral uvula, all going to the superior and medial nuclei, which these are mainly rotatory. You then have the vestigial nucleus and some of the vermion, the spinal portion of the vermis, going to the lateral and inferior portions of the vestibular nuclei, which are dedicated to linear acceleration and static equilibrium. So you can see these two pathways. So through most of the vestibular nucleus, the rotatory component, the angular, is going to be separated from the linear. Not completely, of course. You would, if it were complete, we'd be not schizophrenic, I don't like that term, but we wouldn't have very good balance and coordination as we're trying to play tennis. I always think about playing tennis. So we use tennis when we get to motor, to movement. I will talk a lot about playing tennis. Not that I play tennis very well or at all, frankly, but it's a great example of integrating not only your balance and your neck positions and your momentum with the ongoing somatosensory information, but more importantly, the cognitive function of strategy. Okay, and so all of that information having to be integrated. The game of tennis, probably any sport, truly, but tennis just seems to work for me because we're in motion. It wouldn't. So playing baseball, it doesn't work, right? You're holding still and ready to hit. Soccer, for sure, that would, but you're mostly using your legs. Tennis, again, you're using your legs and your arms, and you have to have integration of movement. You have to know where you're going. To take a swing when you're standing still is nothing like taking a swing when you're running backwards and sideways, okay? And so that's what makes it such a good example for us to think about. And then you also have commissural pathways. One vestibular nucleus inhibits its partners on the other side. The efferent vestibular pathways, efferent, so where do the vestibular nuclei send their fibers? Well, mostly back to the cerebellum. So inferior and medial to the nodulus, uvula, and flocculus, so that the cerebellum can take all of that information that we just saw coming down through the the cortical ponto cerebellar pathway. To have all that information, the cerebellum has to know what is going on. Are we spinning? Are we standing? Are we running? Where does it get that information from? From the vestibular nuclei. So you see the cerebellum is integrating all of that. You also have to have information coming in through the motor cranial nerve nuclei. What's the face doing? I keep saying, what's the neck doing? I wish we were on camera for a moment, because if my ear is down because I'm laying down, is a whole lot different than if my ear is down, even though I'm standing up, but I have cocked my head to the side. That's a totally different world. How is the cerebellum, and therefore the cerebral cortex, how are they going to know that? Well, obviously, I'm going to need proprioception from the neck, because the vestibular nucleus, the vestibular ganglion, certainly has no clue that the neck is turned. But the vestibular nuclei will, okay, and they're going to have to share that and update it with the cerebellar information and tell the cerebellum that this is going on, right? And someone's going to have to provide the vestibular nucleus and the cerebellum, therefore, with all of that information, okay? So all of that is coming in through this very complex pathway, which is both the excitatory fibers are cross fibers, the uncrossed fibers of these cranial nerve nuclei, all the way out to oculomotor, are inhibitory. And obviously, we better know what our eyes are doing. Same thing, take that simple example. If my eyes are in primary position and I'm seeing something in my visual field, there's nothing like if my eyes are dereocha, if they're turned to the side, and I'm looking out of the corner of my eye. If I take a swing in one, the frog is going to have a hard time catching, right, if it doesn't know the position of its eye. And there are no proprioceptive fibers in the oculomotor muscles. Okay, so, well, why do we need oculomotor when we've got vision? Okay, and we know what the rest of the neck is doing, what the head is doing. But there's going to have to be a merger of the visual information with the proprioceptive information, which doesn't come from the oculomotor muscle, but comes from the neck. Okay, get it, guys? This is very complex as we swat the damn mosquito. Okay, that's what we're doing. You can play tennis. I swat the damn mosquito. We will talk about swatting the damn mosquito. All right, so efferents. And then, so the cerebellum is sending information to the cranial nerve nuclei. It is sending information, obviously, down to the spinal levels as we stand, as we run, as we jump, as we kick, as we do everything. we need to know that we are in motion, and we need to know what the momentum of our velocity of our body is, and what the proprioceptive feedback of one muscle is to the other muscle. And we don't want to just be figuring this out in the spinal cord. If we're trying to kick a soccer ball, all the muscles of our legs better act in coordination. And by the way, I don't want to kick the soccer ball in this particular instance. I'm over out on the left wing, and I don't really want to kick the ball in the middle of the ball. I want to kick the ball on its side, put some spin, bend the ball into the net, okay, or to the foot of my teammate. Okay, all of that then has to be conceptualized, not only conceptualized, but then has to be actuated through massive feedback and integration. And the one who finally strikes the ball, which is coming out of the corticospinal tract through area 4, don't know nothing about nothing. It's just telling the muscles what to do. All of the integration of all of the goals, proprioception, position, momentum, has already occurred. All right. And the efferent visual, we were still talking about the vestibular pathways provide excitatory feedback back to the labyrinth. So if it's interested in something, it wants more. Give me more. And probably there are ways of giving me less, because one vestibular nucleus will inhibit the other vestibular nucleus. I want more from this side, less from this side for the moment. Okay, or I want to know more about this side and less about this side for the moment, while the other side is going, no. I want more about my side, and I don't want to hear about your side. Okay, that sort of thing. They all have the ability to shape the incoming information. We will see that better in the auditory system as well as in the somatosensory system. Okay, this diagram is not terribly accurate, but I like it because it gives you the sense that the vestibular nuclei are doing different things. They're going down to the spinal cord, they're going to the oculomotor nuclei, they are traveling into the cerebellum through the inferior cerebellar peduncle, okay? It misses the contralateral, but you get the point. And I created this. I created this using this from Stat Pearls, this lecture on the nuclear vestibular nucleus by Hernandez and Das. These are very recently placed on the web. I'm using a lot of their information. They deserve credit for the work that they did, but I extracted from their much more detailed a series of lectures on this subject, and excellent to visit if you want to. That's why I'm giving you the reference. They're excellent to visit. They're wonderfully written. I've tried to compress their information into a table. That's what I wanted to do, was make a table which tried to organize everything that we just said, because of the complexity of 3 different systems really coming together. And that's it. Yeah. And I thought this was a riot, so I added this last night. My ears were hurting. I should have just said, I'm feeling dizzy, right? I'll change that. Yeah. But the cat doesn't, does it? The cat, you can drop a cat, right? It'll land on its feet. Think about that. Okay, it's turning the whole body. And by the way, there have been movies that follow that. And so you drop the cat upside down, right? What's the first thing it does? Turns its head. Okay, first it rights its head, then it simply reorients its body through its neck and lands. Yeah, right.
And then it cannot. No. Oh my God.
Yeah, it's using airflow. Yeah, the cat here, Punet or something is talking about the fibers or the whiskers of the cat, which are no me gustan las gatas. All right, we're done. Thank you. We're going to see you next week when we will talk about the rostral pons and cranial nerve nuclei 5, 6, and 7. So have a good week, everybody, and we'll see you again soon. Don't forget, an hour at least, okay, before I see you again. Thank you.
Thank you.